My name is Josh Shields, and I'm a graduate student at Michigan State University. I mainly study a highly energetic class of supernova called a Type 1a supernova that produces a large fraction of the ion group elements in the universe and that we use to measure distances to faraway galaxies. These supernovae come from the thermonuclear explosion of a white dwarf, which is a highly evolved star that you get when a normal star like our Sun runs out of hydrogen in its core. Hydrogen is the fuel that the star uses to produce energy, which makes the star shine. And since white dwarfs have no more of this fuel, they are generally destined to cool down and dim for the rest of cosmic time. However, we see many of these stars explode in galaxies around us, and a major open question in astronomy is why this happens at all. We want to know what specific physical process causes white dwarfs to explode as Type 1as. Many popular theoretical Type 1a supernova progenitor scenarios detail the interaction of a white dwarf and some nearby secondary star that throws the white dwarf out of balance by donating material to it. In these scenarios, during the explosion, the secondary will be impacted by supernova ejecta, which makes it look dramatically different from normal stars that we know and understand well. So one way that we can test these progenitor scenarios is by going to where we've seen a Type 1a supernova explode in the past and then attempt to find one of these unusual surviving companions. This is what we did in my recent paper. By combining a large number of Hubble Space Telescope observations taken over many years, we investigated each of the stars in the Type 1a remnant SNR 0509-67.5 and looked for one that showed evidence of interaction with supernova ejecta. None of the stars inside the remnant showed any unusual properties, ruling out the existence of a surviving companion as well as many popular Type 1a progenitor theories for that remnant in turn.